Okay, good morning everybody. I hope everyone's having a wonderful day. So today I'm going to be picking up from where I was last day. Last day I was deriving for you a recurrence relation based on our algorithm for computing factorial. So remember, I'm trying to give you some analysis techniques for recursive algorithms. So I'm hoping to give you a good collection of tips and tricks to do these kind of things. So I'm going to pick up where I was last day. So I'm going to remind you how I formulated the recurrence relation last day, just because we kind of ran out of time last time. So recall in the recursive case of factorial, I have it where I make one recursive call which takes n, the input, and decrements it by 1. So one recursive call happens, and it does a constant number of operations, which is why I have a 1 right here. And in the base case, just some constant number of operations occurs, so I just put a 1 here for the base case. Keep in mind, it could just be any old constant. If you really don't like this, you can always put a c here for a constant. You could write big theta of 1, for example. That's also okay. But is everybody okay with our recurrence relation from last day? So if we're okay with that, I'm going to proceed to try to figure out the asymptotic behavior of this recurrence relation, because we're going to really be interested in that aspect of these recurrence relations probably today, maybe a little bit tomorrow. Not tomorrow, Monday. See, I'm getting really excited about Monday. Okay, so if we're okay with this, I'm going to first show you kind of a classic way of approaching this, and then I'll show you the parallel version using what we call a recursion tree. So the first idea that you may try doing is something called iterative or repeated substitution. And remember, the game plan that when we do this is I try to reapply the recurrence relation over and over again and try to see if I can observe a pattern. And if I see that pattern that tells me for any general term I, that usually tells me something about the general closed form that represents what would be classified, some people call it a solution. Here we just care about the big theta or big O or big omega result. So we don't necessarily have to go all the way and solve a recurrence relation. We just need to know its asymptotics. So generally the idea is that if you're looking at some solution, is generally what you get out of guessing the pattern, and you could check it using mathematical induction if you'd like. So just in here, notice that all I do is I just literally write down the definition for what n is, for n is greater than 1, and then I keep repeatedly applying it and trying to figure out a formula for any n. So notice every time I substitute t of n minus 1, well, this is just t of n minus 1 right here. It's t of n minus 2 plus 1. Now, if you're having a hard time seeing this, just instead of looking at like an n here, imagine I put a banana there. So suppose this was t of banana, and I take away one banana. So now I have a bunch of bananas less a banana. And I keep repeatedly doing this over and over again, applying the definitions. So notice that this right here is just t of n minus 1. So notice I introduce another 1 here. And I can apply the definition to t of n minus 2, which is t of n minus 3 plus 1. And notice that I'm just keeping a counter of how many are separated out of it as I'm doing this. You're going to see a direct parallel over when I do the recursion tree. So this is really one reason why I'm showing you this, is that when I work my way down, notice all I'm doing is I'm substituting in over and over again the definition of the recurrence relation to try to find a pattern. So when I eventually get down to this point right here, I write down this equation here, and I see, okay, well, t of 1 in my definition there is 1. So I have 1 plus n minus 2, which is just n, which of course is big theta n. So from this you can say that the factorial takes time linear in n. So that's how we would go about it with an iterative or repeated substitution approach. We're going to focus on this recursion tree approach, and I'm hoping I could kind of show you the connection between these two. So here's how I'm going to proceed. First, I'm going to draw you the recursion tree. So I've set up some things already, just to get us a general gist of what we're going to do. So the first thing I'm going to do is I'm going to start off with t of n. And what I'm going to write here for a node in this tree is going to be the number of operations that happen in the case for which I just wrote that down. So in this case, notice that the non-recursive work that happens is going to be 1. I'm talking about this one right here. So what I would like to do is I would like to keep track of the total amount of operations that happen at any level of a tree. So every node is going to represent the non-recursive work that happens at that recursive call. So this would be what would happen if I had carried out T of n and I counted up the number of non-recursive operations. However, I have to account for this right here. So it means that one recursive call happens. So one recursive call happens, that's T of n minus 1. So I'm going to repeat this process, and you're going to notice my tree is going to get deeper and deeper as I do this. So I'm just going to do the same exact thing I just did here. I'm going to determine the number of operations in the non-recursive work here. So this is just 1 right here. And then what I'm going to do is I'm going to, then I tell you, okay, there's one recursive call, so I'm going to have one branch. Let me just make these a little clearer. These are 1s. I do one recursive call. That's going to be on T of n minus 2. And this would be level 2 in the tree. If I sum up over the levels of this tree, notice that the work done at this level is 1 again. You're going to see when we do something a little bit more interesting that this is going to be a little different than what I have over here. So I keep repeatedly doing this. So the non-recursive work that happens right here is 1. That means the total number of work that's going to happen here is 1 at this level. And then another recursive call happens. And this process will continue until I reach n is equal to what? Can somebody tell me? When am I going to stop doing this? I'm going to stop when n is equal to what? It's 1. Yeah, exactly. When I hit 1. So if I were to keep doing this, I would end up with a 1 here. And I have another total amount of work done at that level is 1. And you'll notice that for any level I of my tree, it's always going to be that the sum of the work done at that level is 1. But notice that when I hit that base case, it's also 1. Now, we know a lot about trees, right? This is what I said last day, right? We know plenty about trees. So a question I have for you, if I were to consider this entire tree, right now it's not a very interesting looking tree, it's just one big chain of nodes like this. Could somebody tell me what's the height of this tree? What's the height of this tree? And be exact about it. So tell me what the height of the tree is. So I will tell you it is not n. I'm looking for the height. It's n minus 1. Yeah, it's n minus 1. The height of this tree is n minus 1. But the number of levels in the tree is exactly equal to n. So the number of levels is equal to n. So just as a reminder, just in case, just as a small reminder, remember that if the connection between the height versus number of levels, so if you're curious about these two things, that the number of levels in the tree is always going to be 1 more than the height. So if you ever find yourself just questioning yourself about, okay, well, what is this? It's always going to be the height of the tree plus 1. So now this is really interesting because now at each level of the tree, I've actually accounted for the amount of operations that happen. Does everybody see that? So if I were to keep going down, I'll eventually hit some level n minus 1. It will also take t of 1. So it takes t of 1 down here. And in our case, t of 1 is 1, right? Does anybody see anything that kind of interesting between these two pictures I have here? Well, I have that analysis over there and I have this analysis over here. Notice that everywhere I have over here, notice that I have my +1s all right here. All of these. Notice that these match these ones right here. When I count up all of these in relation to the substitution here. In particular, these +1s are exactly these labels I've assigned the nodes. So you might ask, okay, so how can I find a closed form expression for the recurrence relation given this recursion tree? Does anybody have any ideas? Any ideas, anybody? So what would I do? What can I do with the information I have in this recursion tree? So remember, I know the number of levels in the tree. I know how much work is being done at each level of the tree. And remember, all I'm doing is carrying out, in a similar manner I did over there, all of these repeated substitutions. So what do I need to do? Well, think about it. Okay, for each one of these are all of the work done at each level of my tree. So if I were to, for example, sum over all of the levels of the tree, would that represent the running time of fact over there? That might be a good way of approaching this. So why don't we do that? So just to summarize what I've been saying previously, since the height of the recursion tree is n-1, then to compute the total work done, you just simply sum over all n levels of the tree. So if you think about it, okay, so all I have to do now this is the part where I say that the recursion tree is rather effective for making good guesses. Because when I make more complicated recurrence relations, when you're doing this through repeated substitution or iterative substitution, you're going to have to figure out, okay, well, what's happening every time I perform a substitution? Here, because we know plenty about trees, we often will look for some pattern. It's typically geometric, but not always. In our case, for example, it's just simply a chain, right? It's just a chain. Every single time, I'm just going to have it where I'm doing some constant amount of work at each level of the tree. So all I do is I make a formulation that represents each work done. So I look at my work done column. So when I write this part out here, I'm going to try to figure out a general formula for a given level. So that's what that's what I would like to do. So we're going to see in a more complicated example in a moment how we can do that. But let me just do what I just described here. So all I do is I just sum over all the levels. I start at level 0 and I go all the way till level n-1, right? And at each level, the work done, so remember that's the sum of all the recursive work that happens at that, non-recursive work that happens at that level, is just 1, right? Well, what's this? Okay, so I'm going to apply a closed form that I gave you. It's just simply you take the upper limit, you subtract off the lower limit, and then you add 1. And you'll notice quickly here that this is just n, which of course, that's big theta n. So if you ever find yourself wanting to double check your guess, so the part that really is interesting for us is what's going on in that side of this sum. So for us, it's really easy in this example. Other examples, it may not necessarily be. But you notice I get the exact same result. And if you feel like, okay, I want to double check that this sum is exactly the one I want based on the recurrence relation, you can prove this using mathematical induction. So are there any questions about this example? So I will be showing you a more engaging example of a recursion tree in a moment. Right now, I'm just trying to give you the fundamentals. So remember, in my recursion tree, I'm going to draw one out, and each one of the nodes is going to represent the amount of non-recursive work that happens for a given recursive call. And then I'm going to have children. Those children are spawned by the recursion. So by those recursive calls. And each one of those nodes are labeled by what's going to be the total amount of non-recursive work that happens for that one call, each one of the respective children. So we'll see in a moment what I mean by this. So are we okay with this? If you have any questions, don't be shy. Okay, so if we're good, let's proceed. So I want to mention that in the notes, I'm going to provide you 2 more examples of recursion trees. They're going to be based around quicksort. So I'm going to give you an example that's based roughly around when you pick a bad pivot. And then I'm going to give you an example where you pick a good pivot. And believe it or not, using this recursion tree approach, it's actually really simple. In fact, when you select a bad pivot, that's when you get the quadratic running time. It will look almost exactly like my first example here, except the work done will be n instead of 1. And in the good pivot, that's going to be a little bit more interesting. So I'll put this in the notes for you to take a look at. So the big things I really want you to be aware of are, let me just make sure I give us a recap of what we did. So first, you're going to draw the recursion tree. You'll see more what this recursion tree will look like when we do something a little bit more interesting. So we draw the recursion tree. What is the total work? The total work at a level of the tree. So this may in fact be a bound on it, for example. Say, for example, if one of your recursive calls is a little smaller than the other, for example, like say if you have it where you're not necessarily guaranteed that it's going to cleave an integer in half properly. Very often there's mathematical trickery you could get to get around that issue, but you may have it where it's actually bounding it at a given level as well. So another thing that I also want to make sure so what we did here. So the question is, what are the total number of levels in the tree? So you don't necessarily have to do them in this order, but it's rather helpful to do so. Now, so if you address these, you're going to eventually end up with something where I'm going to have some sum that my goal is to simplify it. So when I say this, one thing I must remark for point 3 here is it's very possible to use the recursion tree approach when a recursion tree isn't where it's going to be nicely symmetric. It's going to end up sometimes being lopsided. So when you have cases like this, what will happen is you would bound the deepest side of the tree, meaning the side that goes the furthest down. You'll pretend that the other side is in fact symmetric with it. This is one limitation of using the recursion tree approach, is that you then have to bound a new recurrence that represents the upper bound on the overall running time of your algorithm. So basically, to describe this, let me just give you a quick little picture of what I mean by this. So very often when we draw the recursion tree, you'll end up with cases that look kind of like this, where you'll keep splitting down like this sometimes. However, there's possibilities where you're going to have a recurrence relation where it maybe goes, instead of like that, it may have, say, instead of being it where it's only 2 recursive calls, it may be that one side has 3 recursive calls, then the other one may only have 2. And maybe one finishes a little earlier than the other. So for example, this side that splits in halves may take a little faster to get to the t of 1 before this other side. So the way you would basically treat one of these cases is you would basically pretend that all of this is filled in where it reaches all the way to the bottom. One common way you could do this is just pretend that this side of the tree is in fact this side of the tree. You can just bound it from above. But you end up with a big O result as a consequence of this. So that's just more of a remark. I just want to make sure you're aware of this case. That can happen. I'm going to focus primarily on really nice looking recursion trees today. So another part here is what is the cost of the last level. So sometimes you have it where the base case, the recurrence relation isn't exactly going to be equal to the same thing as in the recursive case. So you have to take this into account. So really it's based around how many nodes are there. We'll see this in my next example. How many nodes are there in this last level? So when you're doing this, this is when you formulate your sum. So this is where you derive a sum, and then you simplify. And from there, that's when you get your, where we start playing around with our big O or big omega or big theta, depending on how accurate we want our result to be. So that's going to be generally the game plan for my next example. So are we okay with this so far? So I'm going to draw you some tree, and then I'm going to start trying to measure stuff about the tree and some properties it has. So this next example will be more of a better idea of how and why you might use this approach as opposed to the iterative substitution approach. So if we're good with that, let me proceed here, okay? So let me define another recurrence relation for everybody. Okay. So here we go. So here's something a little bit more interesting. So here's another example. So we're going to consider t of n is equal to 3t of n over 2. So 3 times t of n over 2 plus n squared, where n is going to be greater than or equal to 2, is a power of 2. You might ask, why am I making that a presumption? It's because it makes it so that I'm ensuring that this tree is always going to have it where I can always cleave n in half. Otherwise, you may have to deal with bounding at each level based on if it's a, because sometimes you might have only a part of a half, something a little smaller than a half, or sometimes a little bigger than a half. But the point is that you end up with something that's going to end, actually typically it's a bottom part, the floor part. But anyways, the point here is that we're going to have it where instead of having where I'm just decrementing by 1 or by 2, it's going to be now taking the input n and it's just going to half it. So here's what my recurrence relation looks like. So I'm just going to assume n is a power of 2. And here we go. So let me just first draw the recursion tree. So first, draw the recursion tree. So as I suggested, for each one of my nodes, I'm going to label the node with the non-recursive work that happens at that call. So the initial call is when I have t of n, right? How much non-recursive work happens when I call t of n at that given time before I invoke this recursive call? Can somebody tell me? So what am I going to label as the root of this tree? So remember, last time I put a 1 there. Remember? That was because that was the non-recursive work that happens when I make that initial call to t of n. So does anybody have any ideas? Well, but what's the non-recursive work that happens here? It's n squared. It's n squared. So I'm going to have n squared at the top here. Remember, that's the amount of non-recursive work that happens when I initially call t of n here. Now, what's going to be a little bit more interesting for us, so I'm going to have Actually, let me proceed here. So now what I'm going to do is I'm going to have 3 recursive calls. Now, I'm going to make this a little wider, just to make sure I have lots of space. So I have 3 recursive calls. That's why we have 3 times t of n over 2. And for each one of those, so each one of these nodes here is going to represent t of n over 2. So now if I look at t of n over 2, how much non-recursive work happens for t of n over 2 before I invoke the recursion? Can somebody tell me or put in the chat? Yeah. So what it will be is it'll just simply be n over 2 where I'm going to square it all. Now, my usual tip with this is that I usually don't recommend simplifying things because it sometimes helps us figure out the pattern. Because remember, this is just to help us perform good guesses for figuring out what the asymptotic behavior of the running time is. And we can always check it using induction afterwards if we really needed to. This method's pretty reliable when it comes to this fact. So if I now were to apply the recursive call here, I should have 3 recursive calls that are all going to happen. What should each one of these nodes here be labeled with? Whoops. So remember, these happen, or imagine you had it where, remember? So imagine I have n as a banana. When I initially called this, I took the banana and I cut it in half. So now all of these are working with banana that is cut in half. So what happens when I cut another banana in half? How much of a banana do I have left? So before I had a half a banana and I half that, so I should have a quarter of a banana, right? Quarter, exactly, perfect. Yeah, quarter of banana. So all of these are going to be n over 4 squared. Remember, each of these nodes represents the non-recursive work that's happening when I make that recursive call. So for each one of these, there will be another set of branches that are going to happen. There's going to be exactly 3 of them until some point. And what point is that, by the way? When do I stop doing this process? What is n? It's at 1, exactly, it's 1. So some point way down here, somewhere down here, somewhere down here, somewhere way down here, I don't know where it is exactly, it depends on n. Somewhere down here. I feel like I'm like putting like icing sugar on a cake or something when I'm doing this. Somewhere down here, you're going to have t of 1, a whole bunch of t of 1s. A whole bunch of t of 1s, which are going to be the leaves in our recursion tree. 1, 2, 3, 1, 2, 3. It doesn't really matter how many are here. We have an actual way we can calculate this out. The point is that there's a whole bunch of these t of 1s at the bottom. These are going to form the leaves of our recursion tree. So I'm going to label the levels. So first, is everybody clear with what this recursion tree represents? Just to make sure we're clear. And where I got these values from. I just want to make sure. So if we're okay with this, I'm going to proceed. Okay, so I've drawn the recursion tree. So just to make this a little easier for us to see what's going on, I'm going to label each level. So this is level 0, that's level 1, that's level 2. And at some point, we're going to get down over here. But I have a question for you. I'm going to skip one step just to make this a little easier because we know a lot about trees, and I'm very confident that you could probably get this one. So what would be, first, an easy way I can ask this is, what is the height of this tree? Does anybody have any good guesses on what the height of the tree is? Now, I'm not asking about the number of levels, I'm asking about the height of this tree, which they're obviously closely related, but it makes it a little easier to remember. Every time I'm halving n, don't let the fact that there's 3 branches here throw you off. Yeah, it's log n. It's log n. It's going to be log base 2 of n. So if you asked me about the number of levels, so I'm just going to note this here. I would write it right here, but it's a little close to the edge there, that the number of levels is equal to log base 2 of n plus 1. Because this is no different than what you may have seen before with things such as, well, this is typical logarithmic behavior. Every time I'm halving what n is. Now, let's figure out what the relationship we have at each level looks like. Now, this is where really what I would consider the tougher part comes in. So this is going to be the work done. So I look at each one of my levels, and I'm going to try to come up with a general formula for any level I. That's going to be my goal here. So before I go there, I want to first talk about these leaves here, because sometimes it's okay to just kind of separate out the leaves and deal with those separately. And that makes things a little easier to work with sometimes. So a question I have for you is how many leaves there are. Now, the answer for this is going to be a little bit strange if you've never seen this before. So it will definitely involve n. It will involve n. But we have to do something with this n. So when I do this, every time, notice that the number of nodes at each level goes up by I always multiply by the previous number by a factor of what? It always goes up by a factor of what? So how many nodes? I'm talking about the number of nodes. The number of nodes. So we're going to care about the number of nodes here. It always goes up by a multiple of 3. Sorry, a factor of 3. Factor of 3. There's a big difference between those two. A factor of 3 every time. So this is definitely geometric-like behavior. But here's the thing. I want you to imagine I were to put in, say, n is equal to, say 8. 8 into this. So if I started off at 8, then I half 8, then I should end up with 4. And then if I half 4, I get 2. And then if I half 2, I get 1. So, in that case, you're going to end up with something that's going to, because we know the number of levels here, well, it's going to be something roughly like, because remember, I only care about how many of these there are. There may be more up here, so I'm going to really care much more about the height itself. So at each level, I have this branching factor of 3. It's a fancy way of saying it. But believe it or not, just for the purpose of the time, I'll let you think about it by taking these two things together. It's going to be n to the power of log base 2 of 3. And at first, this looks a little strange, because it kind of is. But at the same time, think about it. Every single time I branch with a factor of 3, but I need to know how many times this happens. And that actually depends on the height of the tree. So every time I imagine my n, and I want to imagine every time I'm repeatedly applying this multiplicative factor that's going to happen. But I'll let you think about that. But the big point here is that this is the relationship the number of leaves has with this tree's height and the number of branches on each level. So this is just one remark I want to make. It just makes things a little easier to play around with when I just have this kind of sitting on its own. But if you could find a simple way of writing this into the formula, that's even better. It's even better. So let's look at each level. So I have n squared here. Remember, that's the only node that's there, right? So here I have three of these. So I have 3 times n over 2 squared. So I'm going to try it just for the sake of, actually, let's see what happens over here. Let's go to the next one. How many do I have here? I have 9. Each one is n over 4 squared. Now, I want you to remember, we want to come up with a general a term for each level I. So if you're familiar with sequences, what I'm saying is give me a term I that fits the pattern. So if I were to simplify this a little bit, okay, well, you would tell me, okay, it's probably 3 over 4 times n squared, right? It looks something like this when I simplify it down. Well, what happens when I do this? Well, I have 9 over 4 squared is 16 times n squared. But think about it. Think about it. Think about this. What's this? This is 3 times 3 divided by 4 times 4. So when you write this, you can actually write this in a somewhat different way. You can write this maybe as 3/4 squared instead. Does everybody see that? So does anybody have any ideas of what the general formula is? If I give you a level I, does anybody have any ideas of what the formula should look like? So just to make it a little bit more bold of what I'm saying is, so imagine if I were to write this. So if I said this was like that. Does anybody see the general idea here? Yeah, it's 3/4 to the level times n squared. Perfect. So if you find yourself questioning this, you can always confirm it by checking with induction. So this is the idea that I'm going to use. I'm going to combine, so remember I have to sum over all these levels, then I'm just going to incorporate the leaves. But remember, if I have a really nice, simple kind of base case, and I know exactly what that looks like anyways, I can always incorporate that into my sum as well, like in my first example. Here I'm just going to show you just for the sake of seeing something a little different. So let me put this all together. Let's put all this together. Very good, everybody. So I want you to just to make sure it's clear where exactly the pattern is coming from. Notice the work done at each level grows geometrically. So that's the first thing that you should, like when you look at that tree that I have on the board, or had on the board over here, the first thing that should scream to you is that it's a geometric growth. That naturally you're going to find yourself, when you're analyzing this, you might need to use the geometric series somewhere. That's the first thing that should kind of stick out at you like a sore thumb. So what I'm going to just do is I'm going to sum up all the work at each level based on the relationship I've derived over there. So here's what I'm going to tell you. So T of n is going to be equal to 3/4 to the power of 0 times n squared plus 3/4 to the power 1 times n squared plus 3/4 squared n squared. And you're going to keep doing this until you hit just before the final level, because I've accounted for the leaves separately. But if you were to do this and you had a nice pattern anyway, you can proceed anyway to the final level and account for that too, if you felt like it. I'm just showing you this just for the sake of something else, just so you can see this. So 3/4 to the log base 2 of n minus 1 times n squared. Then I'm going to have it where I add this big theta term, and to the, hopefully this is not off the side of the screen, log base 2 of 3. Okay, we're good, we're good. I just right on the edge, right on the edge. So all I'm going to do now is simplify this into a summation. I'm just going to bring this all together into a sum. So I is equal to 0 to log base 2 of n minus 1. So I'm going to have 3/4 times, 3/4 to the I times n squared. And then I'm going to have my big theta term just sitting off to the side. Then notice I have an n squared in here. This doesn't depend on I at all. So I'm just going to factor that out up front. So now this should look like something really nice we can use. So I've just factored out as the n squared. Now, you might ask, Dan, well, we have a nice finite version of the geometric series for in terms of a closed form. You can apply that here, and you end up with something. But I will warn you in advance with this example specifically, sometimes it works out quite nice. In this one, it doesn't look very pretty. It's not very easy to see what the simplification would be in terms of big theta. So I'm going to instead use the infinite geometric series closed form. So I'm going to bound it actually from above like this. So I'm going to do the sum from I is equal to 0 to infinity. Apologize, that says infinity right there is the upper limit of the sum. 3/4 I plus big theta n to the log base 2 of 3. And now this is where I'm going to apply the nice known closed form formula for this infinite sum, because this is a geometric series where the radius, or r, is in fact equal to 3/4. So I'm going to simplify this. So this right here, I can tell you is, okay, this is going to be equal to n squared times 1 over 1 minus 3/4. And then I have the additional big theta term, big theta n to the log base 2 of 3. I apologize if that's a little cut off there. But yeah, if you're wondering where that came from, it was just an invocation of the closed form formula for like this infinite sum here. I've done something like this before. So now all I'm going to do is simplify that down. You'll notice that the term I have over there is going to turn into a 4. So we're going to end up with 4n squared plus the big theta n to the power of log base 2 of 3. Now, if you're wondering, log base 2 of 3 is in fact less than 2. Because, of course, what's log base 2 of 4? That's when it's 2, right? And we know log is an increasing function. So we know that this 2 right here is going to dominate over that term I have over there. So we know right away that this is actually big O of n squared. So believe it or not, if we actually tried using this approach, I end up with big O of n squared. Now you might ask, Dan, why does it not say big theta right there? It's because I've made this gross simplification right here, where I wrote this, I made a strict inequality here. Now, if you wanted to show that it actually is big theta of n squared, you could, of course, use the finite geometric series closed form. You can use that one, but the analysis is a little trickier. If you wanted to use big omega and prove it for big omega, you can do that. And in fact, it will work. So if you were to do that, you should actually be able to show that this is indeed big theta as well. So this is actually big theta right here. I'm just doing this because I made a simplification right here. But analytically speaking, we didn't really do anything fancy-pantsy too much. We just added a bunch of small terms. So the big thing I want you to take from this is that there's really going to be three cases. This is how I'm going to end the lecture. Let me see. In the line, what is the L is equal to the sum symbol, the I. So the, let me just clarify, just in the n squared line. Okay, so this right here, so we have 4n squared. One above it, this one. So this one right here. Okay, so it's from I is equal to 0 to infinity. So I'm bounding this by an infinite sum. Yeah, no worries. No, thank you for asking. Perfect. So let me just recap one small detail. It's going to be important for next lecture, okay? Then we're going to stop right here. So let me just recap one quick thing. Now, you'll notice that in my running time, the reason why I wrote it like this, where you can see the leaves straight out, you will notice that if you look back at this recursion tree, so I'm moving on over here so you can see the tree, I want you to notice that when I actually calculated out my sum over all the levels, which term had dominated the running time? Were it these leaves down here, or was it the root? Could somebody tell me? Which one really ended up winning here? The root did. So there's going to be three cases that you're going to run into very often with a recursion tree. And this is actually going to come up in what I'm going to call the simple master theorem next class. Is you're going to have three general cases that you're going to run into with these things when you have an assumed uniform or equally sized times that you're going to split these problems into smaller subproblems. At least that's how it's going to translate in your algorithms. The first case is when you're going to have it where the running time is going to be dominated by what's happening at the top of the tree. So as the tree gets further down, the amount of work done actually decreases. So that's the first possibility. That's what happened in our example here. The second case is when the amount of work proportionally happens the same at every level of the tree. That's like our first example. And at the third case is what's going to happen is that the number of leaves, which are going to translate to a lot of recursive calls. So if a lot of recursive calls are happening and there isn't a whole lot of work happening, the amount of work done at each level is actually going to increase with the number of nodes as they increase. So when you get down to this bottom, instead of it being something where it's going to get dominated by what's in the root, it's going to be the other way around. So where the number of leaves is going to be quite a lot more than the amount of work that's happening near the top of the tree. So is that clear, everybody? So I want you to think about that. And when we come back next time, I'm going to show you a theorem that actually draws out these three exact cases, okay? So I want to say thank you very much, everybody. And I'll obviously stick around a little bit if anybody has any questions. And have yourself a beautiful day and also a good weekend. And good luck with assignment 4 for anybody that is still working on it. So I'll see you later.